Hey, Physics 30. So we're going to continue on with our EMR wave lessons here, and we're going to talk about refraction. Refraction's it's going to be a 2-week thing because there's a few different things about this. We're going to talk about just the simple refraction, then we're going to be talking about the lens refraction. So using lenses. We're going to have one lab within the 2 weeks here that involves the refraction of light in jello. It's a great lab to do in class because there's jello to eat, but I'll eat all the jello instead. So let's talk about refraction. Now, refraction is the idea of a wave entering a different medium. And as it enters a different medium, and remember if we talked about this in Physics 20, it changes two of its properties of the three. Remember, the three properties of a wave are its speed, its wavelength, and its frequency. So two of them change, but one of them stays constant. And if you remember Physics 20, that one constant piece is frequency. And that shows up down in here somewhere when we talk about the formula. No, but the frequency remains the same, right? And we could see the effects of refraction all the time when it comes to EMR and light, such as this picture of a polar bear here. I got a few other pictures on the side here. This one I just recently saw and read it. So you stand in a pool, your legs look much shorter because of how light is bending as it leaves the pool. It bends towards your eye, and it gives this illusion of things being shorter or longer than they have to be or are. Another illusion would be seeing a coin in two different spots when it's really just one coin, again, because light is coming outside the glass here or coming up to the water and then bending as it leaves the water or bending as it leaves the glass. And both those give you this illusion that there's two coins when there's really one. Or here's the same idea as the first picture here, with if you're looking at something that's in the water, it just looks shorter. So it kind of gives this idea that it could be bending, but it's not really bending. You can see the scale here. It's in, I think it's in centimeters, right? It's 1 centimeter. So you can see that the centimeters have changed size, okay? But they really haven't. They're just an illusion of them happening. So this is happening because as the wave leaves the material, its wavelength and speed change, but its frequency is the same. So the only way to counteract that is it has to bend to keep the frequency the same. If it didn't bend to keep the frequency the same, then we wouldn't see these effects. You would see something completely different. Okay, so this happens when you go from one medium to another medium that have different index of refractions. So index of refraction is just a property of the matter it is that's passing through, the medium that it's passing through. It changes based on how dense the material is, how much medium there is. It's like everything is going to be compared to a vacuum. A vacuum has no medium to travel through, so there's nothing to stop and nothing to resist this motion. Now, if you watch the video here, I put the video on the link at the top here. It's also in the Google Classroom here. It goes to this my physics asylum Nick Lucy guy. That's not really my guy. Sorry about that. He just talks about, does the light actually slow down? The wave property of light slows down. If you talk about it as a particle, it doesn't slow down, but that's beside the point because light behaves both as a wave and a particle. So we could say that the wave is slowing down. So if it's slowing down because of the medium, then that medium, we can measure that index of refraction because it's just going to be a comparison between the two, between that medium and a vacuum, how fast it would be going if it was in a vacuum, right? Whenever something hits another surface, even if it doesn't go, or sorry, if it goes in, so almost as if it looks like it completely goes in, there's always going to be refraction or reflection. Most of the time we don't draw the reflection lines. Some apps that I show you here, you can turn on the reflection lines. You can see what those reflection lines are going, but we usually don't draw those because most of the time, most of the light is going to be refracted inwards when it comes to these kind of questions. Or you have the other way around where most light is reflected outwards. So we don't care about the stuff that's actually going into the material, even if it is, right? So these refractive indexes, like I was saying, is just it's a comparison between the speed of light of a vacuum and how fast that wave is actually traveling at that point. So this can be calculated. This index of refraction, which is denoted by the letter n, is the ratio between the speed of light divided by the speed of how fast it's actually going, the measured speed here. So this is the one on the bottom, the measured speed. Okay. And the top number, C, is just the speed of light in the vacuum. You notice that these numbers here, if you look down here, there's a whole page of numbers here. Vacuum and air are relatively close to each other. If you go with the 2 sig digs here, or the 3 sig digs here, if you get rid of these decimals, vacuum and air are essentially the same. And for the rest of this course, if I talk about air, you can just say it's 1. If I talk about a vacuum, it's also 1. We can ignore that 0.03 at the end. But you notice that all these numbers here are greater than 1. The reason they're greater than 1 because light will always slow down. You never go faster than the speed of in a vacuum. So if my light slows down, I'm divided by a smaller number. The bigger number's in the top. So a big number divided by a small number, you're always going to get something bigger than 1. Right? And as you go through, you can see the different materials here. A good one to just memorize is water is 1.33. Right, so this is a good one. I don't know why I'm writing it again, but this is just a good one to know. Otherwise, I'll just give you the numbers. Like if I ever say it's going between air and ruby, so light is trapped inside the ruby, passes from the ruby into the air, or vice versa, from the air into the ruby, I would have to give you the ruby number. I don't have to give you the air number because the air number is just 1, but I would have to give you what the ruby number would be, right? Or the zirconium or the diamond, etc. So as the numbers get larger and larger and larger, you could determine the measured speed of light in these by just rearranging the formula from before. So remember, these are all just the ratio between speed of light and the measured speed. So I can find the measured speed by taking the speed of light and dividing it by these numbers. So that's how fast the light would be traveling inside each one of these mediums. Okay. You can see most of these are kind of transparent-ish mediums here. Okay. So like I was saying before, if I have an incident ray, you're always going to have this reflected ray come back. So this will always be here, but most of the time we just don't draw this ray. If we're talking about refraction, I just want to care about what's happening inside here. But what we remember for the law of reflection is that if this is my incident ray and this is my reflected ray, they're both the same. The angle is going to be both the same for both those. All right? But you notice down here, the angle of refraction, this R, we'll call this refraction. In this situation, because it's going from a less refractive material, such as like air or something, into something that's a little bit more refractive, like water, it's going to bend inwards here, and my angle is going to change. Now, you could also say vice versa, it'd be going the other way. So if I was going outwards, it would bend outwards, like this way. Again, always measuring towards the normal here. If this is my incident ray down here, this is my refracted, bend outwards because it's going from a more refracted to a less refracted material there. But we can actually calculate this. And there's a bunch of math behind this, but we're not too concerned about the math. I'm just going to tell you what it is. We're not going to derive the formula. To calculate this refractive index, to calculate this refraction angle down here, we use what we call Snell's law. You'll see that a couple slides down from here. Okay, so the next slide just talks about just some general rules. If you're going from a medium with a high index of refraction to a lower one, it's going to bend away, right? So that's the second picture I drew over here, right? So it's bending away. So you can see that the angular incidence here, which is measured towards the normal, and the angular refraction is a larger number. So my refraction here is larger than my incidence. And vice versa, if I'm going from a less refractive to a more refractive, it's going to bend towards the normal. It looks like it's going away from the surface, but we're worried about the normal line here. We're always measuring towards the normal. So in this case, it's bending towards the normal line. So when I say towards, I'm talking about towards the normal line, because that's where everything is measured away in this game, away from the normal line. Okay, so that's important. Okay, so this Mr. Snell here, it's kind of weird because I had a Dr. Snell who was an optometrist, just happened to have the same last name. I don't know why, maybe that's just destiny. But Snell here developed this relationship between the angle of incidence and the refractive index of a material. Now, it started off this way. So n1 times sine 1 is equal to n2 times sine 2. So that's what the formula started off to him. They put all the ones on one side, all the twos on the other side, and you just notice that these two sides are equal to each other. This idea that taking the angle times the the refractive index should be equal to the refractive index and times the sine angle of the other side as well, of the different two sides of the material. And you just rearranged it, and we rearrange it nowadays because there's a reason that we rearrange it this way as well, because we're going to add more to this. We're going to add a bunch of stuff over here later on. We'll get to that in the next video here, or actually maybe at the end of this video. Can't remember now. Oh, it'll be the next video. Okay. So we just write it this way, but you have to note very carefully that it's also on the formula sheet too, that this is 1 over 2. It's 1 over 2, and this is 2 over 1. So these guys have switched from from the denominator to the numerator, and from the numerator to the denominator. They switched here. And other parts of this formula I'm going to add on to this. They don't switch. The only ones that switch here are the n values. For some reason, I can't erase the half that I drew there. Okay, so they have switched. So you have to be very, very careful about where 1 and 2 are. Now again, we draw 1 and 2 here, but you notice up here I used i's and r's. So i's and r's are very similar. You could just replace all i's with the 1 and all r's with the 2, or vice versa. It's up to you how you decide to do that. So it's also just easier if you draw a picture. So imagine you have yellow light, and you notice that I always talk about what kind of light it is in these kinds, because different lights have different index of refractions. So this whole table here is all for yellow light. That's what this table is all for, just for yellow light. Use yellow because it's relatively in this middle of the visible spectrum, but this is just for yellow light. If I use red, all these numbers would change. If I use violet, all these numbers would change. If it was radio waves or ultraviolet or gamma, all these numbers would change. This would be very specific to a yellow light, a very specific wavelength of light or frequency of light. Yeah. So yellow light travels from water into crown glass, and here they gave us the crown glass number at the bottom here. So if you want to go to the table, you could. So I'm just going to draw a picture to represent this. Okay, so here's my yellow light. It's going from water into a piece of crown glass. So this is crown glass in here. Okay. Now I can guess, I can give a good estimate what's going to happen, because water is 1.33. Crown glass, according to this bottom of this table here, is 1.52. Because I'm going from a less dense into a more dense, I'm going to assume that this is going to bend towards the normal. So I'm going to make the assumption that my refractive angle here is going to be less than 35, because my incident angle is 35. Okay, so I want to know what that angle of refraction is as it enters into this crown glass, so this theta r. So to use the Snell's law formula, I have to know what 1 and 2 is. So you just pick either side of this surface here. So if I say the top is 1, that means this angle technically is now angle 1. All right, and this n value for water is now n1. If I said the bottom is 2, then this n value is n2. And the angle that I'm looking for is 2. If I just want to use i's and r's, I can. but I decided to change into ones and twos. So I'm going to go n2 over n1 is equal to sine 1 over sine 2. Okay, so let's put in the things that we know. So we know n2 is 1.52, n1 is 1.33. Here we have sine, and I know this angle, this is 35 degrees. Now you have to be very careful. If your calculator is being reset lately, make sure it's in degree mode. Otherwise, it's not going to work very well. And we're looking for theta 2 here. So I'm going to rearrange this equation for sine theta 2. It's just a cross multiply divide here. So cross multiply divide, I'm going to get 1.33 sine 35, oops, put the degree on the inside, sorry, divided by 1.52. Okay, hold your calculator, making sure that's in the right mode. Yep, my calculator is in degree mode. It's 1.33 sine 35 divided by 1.52. Nope. So we get sine 2 is equal to 0.50187 dot, 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 bunch of decimals there. I'm looking for angle 2, not for sine theta 2. So I'm going to have to go sine inverse. And I get 30. There's only 2 sig degrees here, so 30 degrees. There you go. So my estimation was pretty good. I said it was going to be a smaller angle on the way in than after the interaction with the surface than it was before with the interaction. Cool. Let's try a few more of these. You can see that I have 2 more of these, and then we'll finish off the video. I can't remember when I was going to stop this lesson. Yeah, okay, so this is going to be a 2-part on this one. Light's traveling from air into a transparent material. Oh, what's the index of refraction of this material? Okay, so we're looking for one of the ends. So we have to decide which one we want to do. So it has an incident angle traveling from air. So this is air up here. Now air is 1.00. Okay, the incident angle is 20 degrees. Its refracted angle 17 degrees. So I'm going to assume now, because it's refracted towards, that this n value is going to be bigger than 1. Don't know what it is, though. I'm going to put a little question mark here. That's what I'm trying to find. So you just label the 2 sides. So if I decide this side's 1 and this side's 2, then technically this is n2 then, and this is n1. So I'm looking for n2. And I'll just write out the equation. Now you could always flip the equation over, like that previous one. My sine theta 2 was on the bottom. I could have flipped it over and said sine theta 2 was on the top. But it really doesn't matter. It's just a simple rearranging though. Okay, so let's put these numbers in here. So I'm looking for n2, n1, which is a 1.0, so I didn't really necessarily write that there. This top is going to be the 20, the bottom is going to be the 17. I don't even have to rearrange this because n2 is already in the numerator. So I'm just going to go sine 20 divided by sine 17. I get n2 to be 1.1. I'm going to put down 3 sig digs here because angle sig digs are different than regular sig digs. So I'm just going to say when in doubt, 3 sig digs. So 1.17. And you probably could match this to one of these things up here. Nope, can't. It's somewhere that's between air and ice. I don't know what they are. But sometimes you could match them to one of those materials. There's the index of refraction. Now, if you know you did something wrong, if you got the index of refraction less than 1, it always has to be greater than 1 to be a valid number. Okay, so here light passes from diamond into air. Okay, so diamond into air. So it doesn't matter how you're going to draw this. So maybe I can draw this. I'll draw the diamond up here. So diamond, and this n value for diamond is 2.42. That tells you in the bottom there. So it's going from diamond to air. So I'm going to go, this is air here. His n value is 1.00. Ooh, the angle of refraction as the light emerges from the diamond is 25 degrees. Now we have to think, okay, I'm going from a more dense or a higher index of refraction to something that's lower. So actually, I think this is going to bend outwards. So this is 25. So I think this angle here is going to be less than 5. We're looking for what's the incident angle. So that's this one here that we're looking for, the top one. So what do we have here? So we have to label one of these. Actually, what I'm going to do this time is going to label this I and this R for incident and refracted. Okay. So I have N, I'll write on this side first, sine theta I, which we're trying to find, or sine theta R, which we know, because it tells us the refraction, angle of refraction. So on the other side, you have to make sure these flip. So this would be NR over NI. Okay. So R is 1, I is 2.42. And on the other side, we have sine theta I, which we're trying to find, and then sine theta R, which is 25 degrees. And I could just rearrange this now. This is a little bit easier because I made the theta I on the top here, so I'm going to times it up and divide. Okay, so I'm going to get sine theta I to be sine 25 degrees divided by 2.42. So sine 25 divided by 2.42. I'm going to write the intermediate step here because we eventually get to do the sine inverse. So do the sine inverse of that answer and get 10 degrees. There you go. Yeah, I assumed that the incident would be less because I'm going from more dense to less dense. It's going to bend away from the normal line, so this incident angle should be less than 25, and it was. Looks pretty good. Okay, so we're going to stop the video there. This is only the first part of this lesson. The next one we're going to talk about what happens to the wavelengths, the frequency, and the speed of the waves as we go. We kind of know what happens to the speed, but what happens to the other two properties of a wave. I'll see you in the next video.